Let's continue the virtual work, but for indeterminate structures. So, when it comes for indeterminate structure, so for sure, the requirements will not be calculate a deflection, calculate horizontal displacement, vertical displacement. No, the requirement will again be please draw bending moment diagram with no shear force diagram. Only bending moment diagram, it will be enough. Okay. So what will be the steps? The steps will be copy paste as superposition. The same steps. What was the first step in the superposition? Please calculate the degree of indeterminacy, right? How many reactions here do I have? I have hinged support, so I have here YA and XA, and here it is a hinged support as well, so XB and YB. So I have 4 unknowns, right? And how many equations? 3. So the degree will be 1. So this frame is once statically indeterminate. And we will take both once and twice as we did in the superposition. What was the second step in the superposition? What was the second step? Main system, right? The second step was main system. What was the main system talking about? Please make the indeterminate structure. Please make it a determinate structure, right? So how we used to make an indeterminate structure a determinate one? We used to remove redundant, right? So what redundant here do you want to move? I think we can make any of the 2 hinged supports, any of them we can make it or convert it to a roller support. Let's make the hinged support at B a roller support, so the redundant that I will remove, that I name X, the same as superposition. The redundant will be XB. Right? So the main system will look like this. The hinged support here, it was converted to a roller support, and then the same loads like this. So this is called main system. Okay? What was the third step in the superposition? The third step, you now have a determined structure. Please draw bending moment diagram and name it M node. The same steps as in the superposition. Okay, so in order to calculate the reactions here, I have first to concentrate the uniform distributed load. It is on 2 members, CD and DE. So I have to concentrate this first. 2 times 2, 4, and 2 times 6, 12. I have here XA and YA, and here I have YB. XA directly will be equal to 4 tons, the opposite direction for the horizontal force at C. So XA equals 4. How can I calculate the reactions YA and YB? Take moment either on A or at B. So sigma MA equal. I'll take moment here. So and this direction will be positive, let's say. So 4 times 6, positive, and then negative or positive as well. 12 times 3, 4 times 6, 12 times 3, and 4 times 6 and 1, 7, and then minus YB times 6 equals 0. So YB will be equal to, calculated, 24, 36, 60, 88. So it will be positive. 88 divided by 6. 14.67. And positive, that means the positive that it's in the assumed direction. It's 14.67. No need to waste your time in sigma x equals 0 and sigma y equals 0. No need to waste your time. So sigma y now 12 and 4 is 16. I have 14.67 upwards, so this will be the rest of the 16, that is 1.33. Okay? How can I draw a bending moment for a frame? First, I have to calculate the moment at the joints. Okay? How many joints now I have? I have 2 joints, one at C and one at D. How can I calculate the moment at the joint C? I have 2 directions, either from CA or from CDB, the all of the rest of the frame. I think this will be easier, CA. So it's 4 times 6, which is 24 in this direction. So the other direction, in order to be an equilibrium, sigma moment equals 0. So the other direction will be equal to 24 on the opposite direction. What about the second joint at D? I have 3 directions for the moment at D, either from DE or DB or DCA. 3 directions, so I have to calculate the moment at least from 2 directions. The 2 easier directions will be DE and DB. From DE it will be equal to 4 times 1, 4 in this direction. And from DB, for the column DB, nothing to give moment, so the moment will be equal to 0. So the third direction, it has to be equal to 4 on the opposite direction. Do I need to calculate the moment at any other point? No, for the distributed load, I calculate the moment at the beginning and the moment at the end, and then join the beginning and the end and make the TL square over 8. So, to draw the bending moment diagram here, that will be named M node. Let's draw for each member. For the column CA, the moment at A 0, the moment at C 24 to the right. For the column DB, the vertical member DB, no moment, 0 and 0. For the cantilever DE, the moment at E is 0, the moment at D is 4 upwards, and then join the beginning and the end, and PL squared over 8, which is 2. 2 squared divided by 8, which is equal to 1. The last member, CD, the moment at C, 24 downwards. The moment at D, 4 upwards. Join 24 with 4, and then PL square over 8. Which is 2, 6 squared divided by 8, which is 9. So this is the first moment that's called M node. This is the moment due to loads. Okay? Okay, so now I'm done with M node. What was the next step in the superposition? The next step in the superposition, please draw your main system one more time. Redraw the main system one more time without any loads, because case node was called the loading case. Case node was called the loading case. Case 1 was the redundant case, right? So in case 1, I only put a unit load in the same direction of the redundant that I removed. Here I removed a horizontal reaction at B. So at B, I will put a horizontal force equal to 1 ton. I don't know the direction. I make an assumption here. So I assume that the direction is to the left. So here I assume that my redundant x is 1 ton. I don't know the real value. And then I will calculate reactions one more time and then draw moment again. What will be the moment called? It will be M1, right? Let's calculate the reactions. So here at A, XA will be equal to 1 in the opposite direction. Take moment here at A. So YD times 6 and 1 times 2. So 2 over 6 downwards. So YD 1 over 3 and YA will be upwards on the opposite direction, 1 over 3. Let's calculate the moment at the joints. At joint C, the moment will be 1 times 6, 6. So the opposite direction will be, or the other direction will be 6 in the opposite direction. The other joint at D, from here, nothing, so 0. From down, it will be 1 times 4, 4. So the third will be 4 in the opposite direction. So the bending moment diagram M1 will look like this. Here 6 and 0. Here 4 and 0, 0. The cantilever doesn't have any moment. The beam or the horizontal member CD, here will be 6. And here 4, no any distributed load, so it will be a straight line. So here it's M1 and above is M node. Now I need the condition. What will be the condition? The condition would be at the point that you remove the reaction at. I remove the reaction at point B, right? Okay, so the condition will be at B. Condition at B. What will be the condition at B? The delta 1 node plus x delta 1 equals to 0. This point is not allowed to move horizontally. Okay? How will I calculate delta 1 node and how will I calculate delta 1? This is the only difference between the virtual work and the superposition. The same steps from the beginning to the end, but in terms of calculating the displacements delta 1 node and delta 1, they will differ. In the superposition, I calculate the delta 1 node and the delta 1 using the conjugate beam method. Okay, so let's calculate delta 1 node and delta 1 using the virtual work method. So delta 1 node will be the integration of M1 M node divided by EI dL, and delta 1 the same. So 1 node was the integration of M1 with M node. So 1 will be the integration of M1 with itself, M1 squared over EI dL. So now, in order to calculate delta 1 node, I have to integrate M1 with M node. In order to calculate delta 1, I have to integrate M1 with itself. What will I never see in delta 1? Delta 1. There is something I will never see when calculating delta 1. I will never see when calculating delta 1. No curve. I can see a curve if this is an arch string, the same as in the determinant. But there is something in delta 1 I will never see.
Third degree problem?
No, I will never see a negative sign. When calculating delta 1, you are integrating a diagram with itself, that means that you will impossible, no special cases, see a negative sign. Okay? Let's calculate delta one node and remember the integration. How many members here do I have? I have 4 members. Only 2 of them will be included in the integration because the member DB doesn't have moment at M node, and the member DE, the cantilever DE, it doesn't have moment at M1. So in the integration of M node with M1, there will be only 2 members. CA, the vertical member CA, and the horizontal member CE. Let's start with CA. So now I'm going to calculate delta 1 node. I need a calculator, okay? Here it differs than the determinant. Why? In the determinant, the big equation of the integration, this is the final answer. This is the final answer. You are calculating a horizontal displacement, a rotation, a vertical displacement. So this is the final answer. So even if you didn't put the answer, there's like steps, and this is the final answer. But here in the indeterminate structure, there are a lot of steps to do after you calculate the delta one node. You still will calculate x from the condition, and then you will draw the bending moment diagram. So this is not the end of the example as in the determinant structure. Okay? So delta one node, 1 over EI outside, and then a big bracket, and then a small bracket for each member. For the vertical member, here it's a triangle with a triangle, so linear with linear. So the rule will be L 6 meter over 3x. I factor here is 1, and then the first value multiplied the first value, but they are in the opposite direction, 6 to the left and 24 to the right, so negative 24 times 6. And that's it. Why? The second value multiplied by the second value is 0. First value multiplied by the second value divided by 2 is 0. Second value multiplied by the first value divided by 2 also 0. So what was this? This is the first member, which is AC. You are going for another member, so plus. And please open a new bracket for the new member. I have here a trapezium with a trapezium several times. I told you that this is also called a trapezium with an inverted value. Okay? A trapezium and then a subtracted parabola. So I have here a trapezium with trapezium, linear with linear, and then the trapezium with a parabola, so a linear with a curve. So let's start with the linear with the linear. The trapezium with the trapezium. L 6 divided by 3 times the I factor, which is 4. The first value multiplied by the first value, so 24 multiplied by 6, negative, opposite direction. And then the second value multiplied by the second value, which is here positive because they are on the same direction, so plus 4 times 4. And then the first value multiplied by the second value divided by 2, negative 24 times 4 divided by 2. The second value multiplied by the first value divided by 2 plus 6 times 4 divided by 2. This is not the end of the second member, so I will not put this kind of bracket yet. Okay? The member still have another integration. Okay? So plus. The second integration, the trapezium with the parabola. Okay? What is the rule of the integration of a linear diagram with a curve, a parabola? It's area of parabola. What is the area of the parabola? 2 over 3, the base, which is 6 meters, multiplied by the height, which is the PL square over 8, which is 9, multiplied by YCG. What is YCG? It's the intermediate value in the linear diagram, which is 6 plus 4 divided by 2, which is 5, right? So it's 5. And then divided by the I factor, which is 4. What about the sign? What about the sign? The YCG, which is 5, is upwards, above the datum, right? And the parabola is subtracted, so it's downwards. So up and down, so opposite direction. So here there is a negative sign. And now I can close this kind of bracket. What was this? This was for the member CD. From here, delta 1 node will be equal to negative 415 divided by the pi. Okay? What about delta 1, 1? Integration of m1 squared divided by dl. Always delta 1, 1 is much easier than delta 1 node. When you integrate a diagram with itself, it's so easy. Let's see. Okay. So 1 divided EI outside. Now we are integrating a diagram with itself. So how many members here in the delta 1, 1? You have 3 members having moments. So there will be 3 terms in the equation. The first term, it's a triangle with itself, right? A triangle with itself. 3L, 6 divided by 3 multiplied by I factor, which is 1. And then the first value, so it's 6 times 6. And no signs, no negatives, okay? 6 times 6, and that's it. Plus, it's always plus. The second member, DB, L4. So I will do this kind of brackets. Plus L, which is four divided by 3 multiplied by that I factor is 1. 4 times 4, and that's it. Plus trapezium, right? So linear with linear. L, 6 meters, divided by 3 multiplied by the I factor, which is 4. 6 multiplied by 6. Plus 6 times 4, 4 times 4. Second value multiplied by the second value. Plus 6 times 4 divided by 2. Plus 4 times 6 divided by 2. This is the third member. What was this member? It was for AC. What about this? It's for BE, and the last member was CD. From here, delta 1, 1 will be equal to positive. It has to be positive. 131.3 divided by EI. Now, what is the condition? Delta 1 node plus x delta 1, 1 equals 0. Now I can calculate x. You don't need the value of EI. So x here, I think it will be positive, right? Because delta 1 node is negative. and delta 1 is positive, so x will be positive. 415 divided by 131.3. 3.16. Now I have two ways to draw the final bending moment diagram. The same way as in the superposition, that go to the main example, the one that was indeterminate. Now it's not indeterminate. What was x? X was xb, right? So xb equals 3.16 positive. What does the positive mean? It means that my assumption was correct, so it's to the left. So this direction. So 3.16 to the left. And now you can do sigma x, so x a now will be also to the left, right? Because 4 to the right and 3.16 to the left, so this has to be 0.84 to the left. And then you can, and here 2 times 6, 12, 2 times 2, 4, take sigma MA, and then you can calculate YB, and sigma Y you can calculate YA, and then you can draw the bending moment line. This is the first way. What is the second way to calculate the bending moment, the final bending moment diagram? There is an equation here. M final equals, the same like this. M final equals M node plus X multiplied by M1. M node plus X multiplied by M1. And then I will get, this is the final bending moment. Okay, I will draw it. Okay. This is M final. And then calculate this equation only at the joints. Only at the joints, okay? At joint C, what was the value of M node at joint C? Including the signs. Here, it is a positive moment, right? So it was, so at C, it was positive 24, right? Plus X. What was the sign of X? It was positive 3.16. So positive 3.16 multiplied by M1. What was the value of M1 at joint C? What was the value of M1 at joint C? It was negative 6. Negative 6. Right? So the moment final at C will be equals to 24 minus 3.16 times 6. 5 positive 5.04. So the moment at C positive, what does positive mean? Moment, a positive moment down. So the vertical member here, the moment will be 5.04, and here straight line. Right? What about the other joint at D? Can I calculate only one time at D? Or it has to be 2 times, right? D, E, and then D, B. What about DE? What was the value of M node at DE? The value of M node, where is on M node? It's here, or this M node, right? It was, for DE, it is negative 4, right? What was the value of M1 at DE? 0. So plus 0. Yes, I know that the final moment at the cantilever, I knew it. It's 4. From the beginning. The unknown reactions are not included in this joint. So I know from the beginning that the moment it's called a determinate part, the DE, right? So it's negative 4. What about DB? M node at DB was 0. What about M1 at DB? It was negative 4, so plus x, which is positive 3.16 multiplied by negative 4. So it's 4 multiplied by 3.16, which is
12.64.
negative 12.64. So here, the moment was positive 5.04, and this was positive 5.04, right? That was at C. At D for DE, it is negative 4, okay? At D for DB, it was negative. Negative means? Negative means the tail is upwards, right? Upwards, which is 12.64. So the third direction will be 4 with the same direction of 12.64. So this will be equal to 16.64. Now I can draw the bending moment. Here it's 5.04. Here it's 4 and 0. For the vertical member, it's 12.64 and 0. For the horizontal member CD, it is 5.04 downwards at C, and at D it is 16 upwards, 0.64, join, and then PL squared over 8, which is 9. This is that one. So you have the two options. Either to draw the bending moment using the same way as in the superposition, or using this easy equation to calculate only the moment at the joints. And when you calculate the moment at the joints, you can easily draw directly the bending moment, the final bending moment.